In today's video, we'll be looking at motional EMF and we'll be taking only translational cases. We'll be covering another lecture on rotational motion, EMF in rotational motion. So let's start with the Hall effect. What happens when a conductor is moving in a magnetic field? The free charges. Let's look at this diagram. This is a rod. This is a rod. And this whole conductor is moving in this direction with a velocity v, and there's a magnetic field which is into the plane of paper. So suppose this is an electron. It will experience a magnetic force according to q v cross b. If you will observe closely, the direction of v cross b, v is forward and b is into the plane of paper, the direction of v cross b is in upward direction. But as the charge is negative, the force on it will be downward. So magnetic force will act downward and negative charges start accumulating in the downward side of the rod. So positive charge will remain at this point, and slowly an electric field will build up in this direction. So this electric field will oppose any further segregation of charges. And when equilibrium will be established between this electric force, which is due to this generated electric field, and the magnetic force, when they will balance each other, equilibrium will be established. So we can say at equilibrium, these two forces will cancel each other. QE must be equal to QVB, E must be equal to V into P. Hence, we can assume that this electric field is constant throughout. So we can say the potential difference across the ends of the conductor can be field into separation, which is EMF induced BVL. PV is the field, L is the effective length. So we have derived this result by using a very simple case, but this result is valid for all translatory cases. Okay, just we have to take care of these important points, which is V cross B is directed towards the accumulation of positive charge, hence higher potential. Just get the direction of V cross B, and in the direction of V cross B you will see the ends of the conductor in the direction of V cross B will be at higher potential. We'll be explaining this point in further examples. The second is the induced EMF is BVL, where BVL are the mutually perpendicular components of magnetic field, velocity and length. Again, effective length are there. These are their components which are mutually perpendicular. If they are already mutually perpendicular, take their whole values, but if they are not, we have to take their mutually perpendicular components only. So these two are important points. One is EMF induced will be 0 if any of the two, this BVL, any of the two, BV, VL or BL, any of these two are parallel to each other or anti-parallel. So if they are parallel or anti-parallel, they cannot be, they cannot have any component perpendicular to each other. So EMF induced will be 0. In this case, if they are in the same plane, magnetic field, velocity and length of the effective length of the vector are in the same plane, then also EMF induced will be 0. In this example, there is a rod moving with velocity v and there's a magnetic field which is out of the plane of paper. When we find v cross b is towards this n2, so v cross b is downward. So we can say that n2 will be at higher potential and n1 will be at lower potential. The logic is v cross b will be the direction of higher potential. EMF induced will be BVL as all are already mutually perpendicular. So if we have to find the EMF electric field inside the rod, we can say E induced by L. Okay, in the second example, there's a semicircular wire in which it is moving with a speed u in a magnetic field which is into the plane of paper. we can say the effective length is 2r. So there's a rod, we can consider a rod of length 2r which is moving with the velocity u in the magnetic field B. So we can say that the EMF induced will be BL, which is 2r into u. Again, get the direction of u cross B. U cross B comes in upward direction. So A terminal will be at higher than B, and their potential difference will be the EMF induced, which is B 2r into u. Okay. In the next example, there's a this shaped V-shaped conductor, each having side each of length L, moving with the velocity V in a magnetic field which is into the plane of paper. These two legs are making an angle theta. So we just converted into an effective length which is 2L sine theta. This straight line joining point 1 and 2 will be the effective length of the vector. Effective length is basically the length joining directly the endpoints of the conductor. Okay, so EMF induced will be this PV into effective length, which is 2L sine theta by 2. To get the value which is 2L sine theta by 2, you can just use this result. This make a triangle, right angle triangle. The angle at this point will be theta by 2. So the half of the length will be L sine theta by 2, and the complete length will be 2L sine theta by 2. Again, as the direction of V cross B, V is towards right, left, V is towards left, and cross means inward. So V cross B comes out to be in downward direction. So V2 will be higher. Similarly, in the next example, now the rod is moving at an angle theta with the perpendicular direction to the rod. So we just take the component of the velocity which is perpendicular to the rod. Component of velocity which is parallel to the rod will not be able to produce any EMF because only mutually perpendicular components of B, B and L are able to create EMF induction. So EMF induced, this diagram can be turned into this as if the rod is completely moving with u cos theta only. U sin theta will be neglected because it will not be producing any of the EMF. So EMF induced will be this. Again, with the help of cross product, right cross into the plane of paper will give you up. So V1 will be at higher potential. In the next example, there's again this shaped conductor having a length of 4 meter and 5 meter respectively, and these are 3 points 1 2 3. The velocity of the conductor is parallel to x-axis and the magnetic field is inward. When we draw the effective length of this conductor from 1 to 3, it's come out to be like this, and this will be 3 meter. With the help of trigonometry we can prove that. So L effective is this, but one important thing to be noticed, that velocity and effective length are in the same direction, so EMF induced has to be 0. Any of the two vectors L, B or V, if they are parallel or anti-parallel to each other, EMF has to be 0.